Previously, we had defined work and used that to obtain the work kinetic energy theorem. And although it didn't look like it made problems particularly easier to do, it gets us well on the way to it being much easier to do for certain classes of forces. And those forces are what are called conservative forces. And the definition of a conservative force is a bit tedious, but it's worth spending a moment thinking about it here. So it can be written one of two different ways, and the two ways are mathematically equivalent to each other, but conceptually they might sound a little different. One way to define a conservative force is to say that a force is conservative if the work along all possible paths connecting any 2 points is the same. Any two points is the same. So what that means is, say I pick just any two arbitrary points in space, and this has to be true for all possible pairs of points. So let's just call these 2 points A and B. And what we're saying is, if we imagine that our object moved from A to B and there was some force acting on it, let's say this at this point here, that force was pushing like that. And this can just be any arbitrary force whatsoever. If we go and calculate the work done along this path, and then say we go and take a look at that path that connects A and B, let's say right at this point here, that's what that same force was doing. The work along this second path here has to be equal to the work done along the first path. And in fact, for every possible path that we could imagine between A and B, the work would have to be the same. And for every possible pair of points, A and B, it will be the case that the work will be the same for that pair of points. Now, for a different pair of points, of course, it'll be a different number. But for any pair of points we pick, every possible path that connects the 2 points, if the work done by that force on the object going from A to B is the same, then we say that the force is conservative. Now, it sounds like it would be almost impossible to show that a force is conservative, but it turns out that although it can be a little tricky, it's at least not as bad as it sounds at first blush here. Another absolutely equivalent definition, and you can show that the two amount to the same difference, is to say that the work done on all possible closed paths is 0. And the idea goes like this. Let's say that I reversed the direction of this second path. Then what I could have is a path that went like this and then like that. Well, if I reverse the direction, then everywhere what I've done is I've flipped the direction of my ds in f dot ds in my dot product for work. And that's going to make a negative. So I'll do positive, let's say 17 joules of work here. Then on the return path, if I go back, it would be negative 17 joules. So if I go from A to A along a closed path, the work would be 0 if the force is conservative. This turns out to be handy as you go along in your math. If you end up taking vector calculus, it turns out that you can show that this is the same thing, saying that a mathematical quantity called the curl of the force is equal to 0. But that's beyond the scope of this treatment here. So it sounds like it's pretty terrible to show that a force is conservative. So let's at least start by identifying an example of a force that's not conservative. So to be a non-conservative force, all you have to do is find literally one example where the work done along two different paths is different. Or conversely, that find one closed path where the work done is non-zero. So let's just take a look at the poster child for non-conservative forces. And then we'll get back and take a look at an example of a conservative force in a bit. Let's take a look at friction. So let's just imagine that you've got your physics book and you slide it along a table. So there's your physics book. So it starts here. This will be our point A. It'll end here. That'll be our point B. Now I'm going to take a look at two different paths. The first path I'm going to go and take a look at is just plain the straight up delta R, like that. I'm going to actually just call this distant. I'm not going to call that displacement just yet there. I'm just going to say that let's call this distance here delta x. There, that's a little better. All right. Now we can find the work done along this purple path. The work done by kinetic friction here. Yeah, obviously not static here. We're looking at kinetic. So the work done along the purple path is going to be the force of kinetic friction times delta x times the cosine of the angle between kinetic friction and our displacement. Well, we can go ahead and map that out real quick, figure out what that angle is. So here we're displacing it to the right, so that's my delta r. And my force of kinetic friction, since it opposes the motion, points straight back. That makes the angle 180 degrees. So then we're going to be saying that the work done is the force of kinetic friction times my delta x times the cosine of, times the cosine of 180 degrees, which that cosine is -1. So the work done along the purple path is minus the force of kinetic friction on it times delta x. Great. Now let's just think about some other path. Instead of taking the direct straight line path, let's have our pink path here. First go straight down, like so. So this will be segment 1 of my trip. And then from there, we'll go on to segment 2 of my trip. And then straight back up to, let's try making that closer to the same length. Yeah, that's pretty good right there. There, oops. There we go, much better. All right, so that's this leg here will be segment 2 of my trip. And finally, this leg here will be segment 3 of my trip. And that gets me from A to B by taking a detour. Well, the length of this bit of the path, segment 2 of the path, is the same delta x. Now we'll just say that the distance traveled along Step 1 and step 3 are both delta y. All right. So along the pink path, the work done by kinetic friction would be the work done along the leg 1, plus the work done along the leg 2, plus the work done along leg 3. All right. So along leg 1, that's going to be the force of kinetic friction times delta y. And now, along leg 1 here, my delta y, my delta r is pointing down, my Fk is pointing up. It's still a 180 degree angle because we're opposing the motion. So it'll still be a cosine of 180 degrees. So that's leg 1. Leg 2 is exactly what we had here. So it's going to be Fk delta x times the cosine of 180. And then for leg 3 will be Fk delta y. And again, here along this leg, my delta r is pointing up, but my force of kinetic friction is pointing down. So again, it's a 180 degree angle. So again, we have a cosine of 180 degrees. Now, all these cosines are -1. So we got two terms with the Fk delta y. So this becomes minus 2Fk delta y. And then we got this term here, which is minus Fk delta x. Now what's important here is that is not the same as what we got along the purple path. It differs by this extra amount of work that friction did to the tune of minus 2Fk delta y. So that's it. You literally just have to find a pair of points, so there they were, A and B, for which just two different paths give you a different answer, and that means that friction is non-conservative. All right. Now let's go and take a look at an example of a conservative force. We'll take a look at gravity. And specifically, we'll just do gravity near the surface of the Earth, or near the surface of a planet. So we can model the force of gravity as being straight down. In a later video, we'll take care of the general case. So, showing that a force is conservative means that we have to show that for all possible paths connecting two points, that you will get the same, that for any pair of points, all possible paths will give the same work, and that nothing breaks regardless of, I'll always get that to be true regardless of the pair of points I choose. And that's a bigger lift, but I'll be not quite as rigorous as I could, but I just want to give you a flavor for the argument, and I will be kind of waffling on it just a little bit. But let's again just think about taking our physics book. So what I'm imagining is that here it is. Now, before we were doing the horizontal plane, this is the vertical plane, just to be clear. So this is my point A, and I'm going to move my physics book over here. This is my point B. Okay, so let's just start by, again, taking the direct path. So there's my displacement, delta r, and I'm just going to say that is the path I took to move the physics book from A to B. All right, well, we can map this out. Everywhere along the path, the force of gravity pointed straight down. And to a much smaller scale here. Oops. And I'm just trying to draw something parallel just to get angles. This is my angle phi. Now, since the force is a constant and our path is a straight line, we can say that the work done by gravity here is equal to the force of gravity dotted with the displacement. So that will be the force of gravity times the displacement times the cosine of the angle between the two. When I put them tail to tail, that's phi. Well, if I go and look at this diagram here, I'm just drawing a horizontal and vertical line to complete a triangle here. This angle here, theta, is that would be my angle phi there, same as that one. So this angle theta here is 90 minus phi. Okay. So I can remember that the cosine of an angle is equal to the sine of 90 minus the angle. So this will be FG delta R times the sine of that angle theta. But the sine of that angle theta is this distance right here. So this distance right here, actually let me move it off to the side a bit. This distance right here is my delta R sine theta. Oops. There we go. Delta R sine theta, or if I prefer, delta R cosine phi. And that's just this vertical distance right here. Looking ahead, I'm going to just observe that the y-coordinate changed from some value y initial to some value y final. So this distance here, the way I've got it dimensioned, and I promise it works for all possible cases, but the way I've got it dimensioned here, this is this delta R sine phi here is going to be equal to, I want to write it as a delta y, so I'm going to say y final minus y initial, but if you look at that, that would give me a negative number, so I have to put a minus sign there. All right, so with that, along the purple path, this works out to be the force of gravity times times minus y final minus y initial. There we go. And the force of gravity is, of course, mg. I'll pull the minus sign out and have minus mg y final minus y initial. And hey, that's just a change in y. So I will write this as minus mg delta y. So that's what it is along that path. Now, very quickly here, I could take a look at, say, another path. Just let's kind of take the obvious one. Let's go straight horizontal and then straight vertical like that. So this would be leg 1, that would be leg 2. All right, well, along leg 1, for my blue path, here, let me make all of that purple. There we go, much better. So in leg 1 along the blue path, the displacement is straight to the right during leg 1, with the force of gravity being straight down. It's a right angle. So we remember that a force that's perpendicular to the displacement does no work. So along leg 1, the work done by gravity is 0. Now, let's look along leg 2. Leg 2 is where we go straight down like that. So that's going to be my delta R pointing straight down like that, and gravity also pointing straight down like that. That's going to give me an angle phi that's equal to 0. So the work done will be equal to the force of gravity times this vertical distance, which we worked out is minus delta y. So once again, we get minus mg delta y. Well, that's promising. So we've gotten that at least for the straight line path and the horizontal vertical path, the work done by gravity along both paths is exactly the same. All right, that isn't even close to good enough, unfortunately. We have to look at the general path that connects the 2 points, but I can give a bit of a flavor for how to think about that. So let's make the general path some sort of a orangey color. Yeah, there we go. So this is just some totally arbitrary general path. Oops, I did not mean to do that. All right, let's just try. There we go. Yeah. There. That's just some totally arbitrary general path that connects A and B. Now, the thing is, we have to think about every conceivable path, including ones that loop around on each other and all of that. But what I'm going to try to do is argue all at once that this is still going to give me the same minus mg delta y. And the idea goes like this. The general form, the general way that we're going to get the work along such a hideous path is to say that the work is going to be the integral of the force of gravity dotted with differentials of displacement along my path. So let me just copy paste my path. There we go. Oops. There we go. Something like that. So what we're saying is, like, we're imagining to evaluate an integral like this. It's the same kind of idea as doing a more standard integral that you would be familiar with from calculus. So you would still be dividing things up into tiny little steps and then adding up all of those tiny little steps. The only difference here is that what you're going to be doing is picking out little steps, ds, like so. And you're going to have a zillion of them all along here. So say right here, the force of gravity is doing straight down. My ds is to the right and just a shade up. If I pick another point, say right here, my ds is kind of doing that action right there. And my force of gravity is pointing straight down. So the force of gravity here is a constant, and it's always straight down. So what's going to be happening as we go along and add up all the possible DS's all the way along this god-awful looking path is we're going to evaluate what F dot, the force of gravity dot ds looks like for that step. Well, we can do that actually. That is going to give me the force of gravity. And remember, one way that we can interpret the dot product is to say that it's going to be equal to the one of the vectors times the other, the component of the vector that's parallel to it. So this ds here, the bit that's parallel to my ds right there, and here let me just draw this in jumbo vision right here so we're really clear what I'm trying to do. So there's my FG right there. Here is my ds right here. What we're going to be doing is we're going to be dropping, here we'll use pink, perpendicular down. And this piece right here, dy, the dot product is just going to be FG times that piece dy right there. That's, that's coming from us saying, if you remember from the dot product identities we had earlier, that's coming from saying if I have my vector A and a vector B like that, we could say that A dot B is equal to A times B parallel, or B parallel was the piece of B parallel to A. So this is exactly what I'm doing here. I'm taking ds, and the piece of ds that's parallel to the force of gravity is the change in the y component. So that's where we're going with this. So a calculus professor would be wincing just a little bit right now because I am sweeping some things under the rug, but the spirit of the argument is correct. So I can turn this into an integral just saying that this is going to be equal to the integral of fg times dy evaluated from y initial to y final. Well, the force of gravity is a constant. It's equal to mg. Sorry, y final. And yeah. So you get mg integral from y initial to y final. Yeah. And this is dy. Well, again, to just graphically evaluate that integral, we're literally just evaluating the integral of the number 1 from y initial to y final. So literally the area is just going to be equal to y final minus y initial. Now, the way I had this set up, however, I need to get into our delta y that we had before. If we take a look, my change in y coordinate is negative, but I need the work to be positive. So when I write it in terms of the way I've had my delta y defined from before, this is going to be minus mg delta y, which is what we had before. Now, the next bit of mathematical sleight of hand is for me to say that, okay, I showed it for this particular path, and there's absolutely nothing whatsoever that changes the logic that I did going from path A, from point A to point B, for any path that connects those, any path that connects those 2 points. I'm just saying, gee, that sure looks reasonable, so I guess we're done with that. All right, so we've seen that gravity is a conservative force. I'm also just going to assert, I don't want to drag people across broken glass any more than I have to. I will also assert that the spring force is also conservative. I figure it's a similar kind of argument to this. I don't think it will create any more enlightenment. And I would have to do just about the same amount of sleight of hand that I did here, where I intentionally had to put a couple mathematical details under the rug and just sort of give you the flavor of the rigorous argument. But let's go and revisit why this is going to be a big deal when we introduce potential energy in the next video. The reason why this is going to be a big deal is because since the work done doesn't depend on the path that connects the endpoints, but just on the endpoints themselves, what we hope is that somehow you can find a function that only depends on the endpoints, where the difference in the value here and here is related to the work done by the conservative force. If you can write such a function that only depends on the coordinates, on the configuration, on the force involved in the configuration of the players, basically, that's a lot easier to do than evaluating an integral every single time, or having to think very carefully about how the force is pointing and the displacement is pointing, all that. You'll just be able to plug and chug into an equation. So that's where we're going in the next video, when we go ahead and properly define potential energy and get to the work energy theorem, which is distinct from the work kinetic energy theorem. All right, I'll catch you in the next video.